times K. Why are both common? I don't know, because nobody can agree on anything. But it depends on, so the units kind of tell you, so this is, you know, moles of A per liter per time is the rate, right? That part is unambiguous. This is what the rate equation means. So it depends on, are the units of K written as, make sure we get this correct, are they written with a basis of 2A or 1A? And that's where the 2 comes from, is one of them is going to have liters per 2 moles of A, and then you're still going to have the inverse time. And then one of them is just going to be liters per mole inverse time, where mole is left ambiguous based on, you know, just mole of reaction.
Gotcha. So it's a basis of how they define it.
Yes, it's exactly that. It's how do you define the rate constants. And again, since I didn't define it, I didn't think about maybe people will put the 2's in there.
Gotcha.
So that's why you're going to get full credit back. And notice that it actually doesn't affect the first part of the problem, right? The first part of the problem doesn't require rates. Now, that's not to say you couldn't have solved it that way. It's entirely valid to say, now I'm going to set this equal to 0 because I'm at equilibrium. And what do you get when you do that? Well, you get Ka over Ka minus 1 is equal to, move this over, and you get and this is equal to big Kp. Now let's do the same thing, but with the 2's. You get K1 over K negative 1. Again, here I'm using Vogler's notation, so I have to include the 2's. 2 times B times C, 2 times A. Sorry, this is supposed to be squared. That's squared. And as you see, the 2's will cancel out, right? So it shouldn't have stopped you from solving the equilibrium part. All right, so again, without the 2's, the final form, once you do the stoichiometry part, okay? And again, if you set this interior part to 0, you can rearrange, solve for the equilibrium conversion that way. So that's another way. I think Vogler uses that approach sometimes when it comes to solving for equilibrium conversions, is he writes out the rate equations. I just start from the definition of an equilibrium constant. I find it easier. All right, where's my statement? Sketch a Levenspiel plot for this reaction. So I move the concentration over just because we can't solve for it, right? We had a couple of examples like that. So is this Levenspiel plot going to increase, decrease, or be constant? It's going to increase. Where does it stop? At what conversion? Right. So a lot of people had it go all the way to 1. It does not go all the way to 1. It stops at equilibrium. What is its value at equilibrium? Infinity. The rate is 0. 1 over 0 is infinity. What is it on the other side? Nobody lost points for this part, but what is it?
Goes back to the inverse.
It's going to go back to 0, starting at negative infinity, right? And this should be going to 0. Sorry about that. Okay. Clear there? And yeah, this is at 0.79. And so then it asks, which reactor would you prefer to use? PBR, right? Because this is increasing, you want to use a PBR because it gives you the area under the curve instead of the area of a rectangle. Okay, part C was 5 points. 2 points for PBR, almost everybody got that. 3 points for having this generally correct. Although, like I said, you didn't lose any points if you left off the negative portion of the Lagrange plot. So any questions? Okay. I think the third problem was hurt by its position on the test, because I actually think it's more straightforward than the other two, but it came at the end. So, well, I'll give you the statistics. The second problem was out of 30 again, I think. The average was 19.9, the median was 20, the modal score was 24, the standard deviation was 5. Okay, the third problem, there's a picture. The reaction is 2A goes to B plus C. Okay, this is a fluidized bed, CSTR. So there's catalyst in there. 2 packed bed reactors in parallel with a valve in between that splits flow between the 2 PBRs when it's operating properly. All reactors operate at the same constant temperature. So isothermal. Pressure drop in the CSTR is negligible. Pure A is fed to the CSTR at a flow rate FA naught. And the CSTR achieves %30 conversion. All right, any questions about the setup? Okay. The valve has malfunctioned. All gas is flowing to PBR-A. PBR-B is not doing anything. Derive an algebraic equation of the form A equal to some function of conversion equal to G, which is a function of catalyst weight. And that form relates the conversion to the catalyst weight in PBR-A. And then there's another part here where it says where this is defined with respect to the inlet of the PBR. Okay, Here, A is a constant, and as it goes on to say, f of x and g of w are functions of only the conversion of the catalyst weight. Clearly define all parameters in your equation to get full credit. All right. So for this part, we can ignore everything except PBRA. Because the conversion is redefined based on the inlet to PBRA, it doesn't matter what happens upstream. It's irrelevant. So where do we start these problems?
You can't start with the FA naught from all the way to the left.
No.
What if you do the x from point 3 to the ux? That's what they did in the book.
You do, the problem statement says don't do that.
Shouldn't it be the same though?
It's not going to be the same. It's going to be similarly correct. If you did it correctly, bring it to me and I'll see. But it literally says don't do that, right? It says just treat it as if it's isolated. Okay, so the design equation is FA naught A, meaning this feed. And I doubt anybody lost points if they didn't leave, if they, just put FA naught there. And then dx dw is equal to the rate. And the prime just means that it's a rate based off catalyst weight instead of volume. So then we go to stoichiometry. So the concentration is equal to the flow over the volumetric flow rate.